Hi, in this video I'm going to give you a quick introduction to Thompson's groups and the Dehn function. So Thompson's groups were introduced in 1965 by Thompson. So he introduced three groups called F, T and V, which are one the subgroup of the other. So I'm going to give you a quick definition of F and T, which are the groups that appear in this paper. So Thompson's group T can be defined as is a group of self-homomorphism of the interval of the circle. Sorry. So here by circle, here I mean I think of the circle as the interval 0, 1. Where we identify 0 with 1. So in this setting, Thompson's group T can be seen as groups of self homomorphism of the interval, which are piecewise linear and positive. And they also need to satisfy some additional conditions, which are the following. So F has well-defined derivative, except at finitely many dyadic points. So rational points where the denominator is a power of 2. And F prime is power of 2 wherever defined. One can also see T as some certain group of automorphism of the binary rooted tree. In the paper, we will use more this interpretation as piecewise linear homomorphism of the circle. And in this definition, it is quite easy to see how F is a subgroup of T, because F is just defined, can be defined as the subgroup of T that fixes the point 0 or point 1, which are identified. So it's the same as T, but here instead of S1 we just have the interval, basically. Right, so these are the two groups that we study in this paper, and an important thing is that these groups are all finitely represented, even if they somehow present some recursive behavior. For example, F contains a copy of F times F, and V contains a copy of V times V. So they exhibit this kind of recursive behavior. They are still finitely represented groups. And which leads us to the definition of the Dehn function, because the Dehn function is a quite important quasi-isometry invariant that is defined for finitely represented groups. So since these three groups are quite studied since their definition, it's interesting to also understand the Dehn function as an invariant. So the Dehn function so Dehn function. So the Dehn function is, as I said, a quasi-isometry invariant associated to a group. So it's a function delta G from the natural to the natural associated to a finitely presented group G. And there are two ways I like to see. I'm not going to give you the precise definition, which you can find in the paper, but I'm going to give you two ways to think about it. So there's a geometric point of view. You can think of it as a optimal isoperimetric inequality. So let me be a little more precise. So if G is the fundamental group of a compact Riemannian manifold, then delta G is an optimal isoperimetric inequality. As a parametric function, meaning that gives you an estimate of how big the area of a so given a loop of length n, delta G of n is the maximal area, like the area of a minimal fill-in disk for that loop. It's an upper bound for the area of a minimal fill-in disk. Where the area is, of course, with respect to the Riemannian metric. And there's also a combinatorial way to see this. So if one fixes a presentation, so delta G of n is the number of relations needed to show that a word of length n represents the trivial element. So relations are morally equations that hold between words in the group, and if you have a word that represents a trivial element, it means that by using a certain amount of this relation or equations, you can reduce it to the trivial word. And delta G of n is precisely an upper bound of how many of these words, of these relations you need. So it's somehow a quantification of the word problem of the group. And if one looks at which kind of function can appear as a Dehn function of the group, there's an interesting situation, because so if one thinks of all possible functions on a line, then it turns out that so the Dehn function can be linear. So here are hyperbolic groups. So hyperbolic groups can be characterized as exactly the one that have linear Dehn function. Then somehow we see a gap between linear Dehn function and quadratic Dehn function. But then after linear, there's a dense possibilities. The functions that can arise are somehow a dense set. So any kind of behavior is possible after quadratic. And a lot of groups have quadratic Dehn function. For example, cat-zero groups have quadratic Dehn function. And Thompson's groups are also conjectured to all have quadratic Dehn function. So Thompson's group F was proved to have quadratic Dehn function by Kuba, and in this paper we show that T has quadratic Dehn function. All right, thanks for listening.